Next part of today's lecture is about images. So what are images at all? So very abstract. It's some kind of pairing between a spatial information, location of something, and some kind of information, a value. So it could be an intensity of something. In most cases, we are talking about 2 or 3 dimensional data. But in some cases, we can even go up to 4 dimensions. So then we would add the time dimension in it, or maybe a spectral dimension, or possibly 5-dimensional. That is something that's coming now in the neutron imaging, that we produce tomographies with spectral information over time. So that would be the 5th dimension then. Images. They are sampled in a way because the real world is continuous. There are no stepwise information in the real world, usually. And there are no boundaries. But the computer needs to, or the detector needs to limit, first of all, the dimensions of the image. So it has a limited extent. And also, in order to bring it into the memory, you have to have discrete levels. So in the continuous world, we have some kind of soft curve as intensity, and we have also a continuous space. What we need to do is to discretize the whole thing. So the levels, they will be stepwise with some number of bits. And so levels actually. And also the image itself needs to be rasterized into a grid. And looking at this example, you can see, first of all, if we have the original image, looks like this. Maybe you do a downsize, factor 2, you still don't see much of the difference. But if you do a heavy downsize, you start seeing that everything gets pixelated and you can't resolve fine features anymore. So you have to decide which pixel pitch you have and also the resolution of the system that acquire the data in order to capture the information you need. The other thing is how many levels you use to discretize the gray level information. In this original data, it's actually a floating point image, so I don't really know how many gray levels it has. But in this case, I discretized it to 16 levels. Still looks pretty decent. And maybe it's sufficient for some applications and it would save you a lot of data if you can do it. Going on 4 levels, well, then you lose information. And the question is, how many levels do you need to represent the information you have in your image? Usually what is acquired in scientific experiments is that the camera takes 16 bits. You may not need or use all of them. But I would say at least 256 gray levels or upwards. So in a good illuminated image, you may have 40,000 gray levels, and then you can start having some, doing some real good quantification and processing on it. But in some cases, you actually are happy with this one. For example, if you have done some segmentation, classification, then you already have just a few regions that you know this is, for example, whatever, bones, that is cartilage, that is fat tissue, then you only have 3 classes, and then void around it, so you have 4 classes. Then it's enough with 4 levels. But if you have something that you acquire with the imaging experiment, then you should aim for a lot more gray levels to have good statistics in the data to do good segmentation. So let us create a little image, just a little test image. We have some positions, so this is just a row X. Actually, I should have shown this code. So let's look at the code somewhere. Is it? It's hidden. Anyway, here comes the image. should go back. So this is the first row of the image, and you can look at it like this. So just some random random values in a 4x4 image with 100 gray levels, so it's not so interesting. The notebook is doing stuff. Okay. So, let's go on that one and that one. So the other way would be to look at the image with some colors. It's more interesting, maybe. It can help you to detect some features. There is an interesting paper from Rogovitz from '96. Actually, the title is How Not to Lie with Scientific Visualization, because by setting different colors on the images, you can more or less invent features in the data that can be misinterpreted. So some people claim, oh, we have a film around the sample. It's really actually just a visual feature from the color map. And that is very important to know when you start using color maps, that you can actually show things that are not real in the data. And in this case, I used just a blue color map, ranging more or less monochromic through the blue color line. And well, you can always define the color map however you like, but there are some good ones to select. So a classic one that comes with many software packages is the jet map or rainbow map. Don't use it, please. It's horrible. So it comes sometimes by default, but try to avoid it because it's not very good for the interpretation. It can really introduce new artifacts. There are several articles about why you should not use it, and I have linked some of them. That is really one that you should avoid, because one thing is that it doesn't print well when you do print it out on a normal printer. It's not interpreting the intensities in the right way, and that can be very confusing when you print it out as grayscale. The other thing is colorblind people have problems with it, and so on. There are many motivations for it, and even lectures about color maps where they say never use the rainbow map. Another one that is popular is the so-called hot map. It's going through from black to red to yellow to white. That's pretty useful, actually. And then if you go in Python, you can see that there is a lot of different color maps. Some are continuous. Some are like diverging. So if you have something that has a positive and negative side, these can be useful. Just make sure that you have the midpoint on the right place. So you have to scale the data symmetrically. And then there are qualitative color maps, usually useful when you have done segmentation. Then it's a good way. As you can see here, they are alternating a lot. So you have a good contrast between two numbers that are close to each other. So for example, if you have done a labeling on an image, and apply a continuous color map, then it's very hard to distinguish, is this label 1 or label 2. If you use this one that you have down here, you can see directly this is one object and this is the other object. So these color maps, they help you to get better understanding of labels. And then there's a lot of more strange ones. The one that nowadays is the default in, let's see if I can find it. This one, the top one here, Viridis, is the one that is the default in Python. In MATLAB there is a similar one, but of course the inventors of this Viridis map say theirs is better in some sense. But it's essentially something that goes through black, blue, green to yellow. And that one has been verified to work well also for colorblind people. But color maps is essentially just a mapping of the gray value or the intensity value into a color. So you don't start to interpret more into it. It's for the purpose of visualization, to detect things in the data, but that is it. And some different color maps look differently when you look on the different color channels. So we have the red channel, green channel, and blue channel. In the computer, normally the colors are represented by the red, green, and blue channels. There are other color map schemes, but the typical one that most data is stored in is the RGB scheme. And here you can see a little bit how the intensity varies for the three channels. The other thing you can do with these color maps is to put some weighting into the interpretation. In some cases, you want to have some weighting like this, where you say it's saturated at some point, and then that's it. Or in other cases, you can see that this has a logarithmic scale, and that can put emphasis on different parts of the intensity in the image, and that you can see on these images. So here you have the original data. You apply the hot color map, or you can apply also this logarithmic lookup table. And that enhances more the dark regions. So you can see here this is very dark compared to the bone structure, and it becomes a bit brighter in this way. So you can shift the intensity or the focus of the gray levels in the data. And actually the logarithmic or exponential scale is what is called gamma correction in many image processing programs. Like, for example, Photoshop, you have something called gamma correction, and then you can pull it in either direction you like. Yeah, then we have the 3D images. Until now I've only shown, and I will mainly show a lot of 2D because it's easier to show on the screen, but a lot of processing is actually done on the three-dimensional data. And we have two cases of three-dimensional data normally. We have the volume, the real actual volume, or we can have a movie, a time series of 2D frames. And the analysis is the same, how you can work with it. But the advantage for the time series, observing it as a volume, is that you can extract slices in the, for example, in the Y time scale. So if you would have a bouncing ball, on the XY screen, you would only see something going up and down like this. But if you look at it in the time scale, you can really see that it follows a sine curve instead. And that is something we have been using in our experiments, where we look at, for example, water uptake in porous media. And the capillary rise follows the law of square root of time. And that can very nicely be seen if you look at the height to time dimension. So this is a very nice way of visualizing it, and also being able to filter data in the time direction also can help for getting the data more easier to interpret. The three-dimensional image in Python looks something like this, and this one I actually want to show. So let's see where I get this one and unhide. Oops. So, in this case, it's just, let's go back. So, in this case, again, I'm just generating some image. It's just a range from 0 to 26. I reshape it into 3 by 3 by 3. So I have a volume, and this is what it looks like when you print it out in Python. So it's essentially, it's just two-dimensional images in a row. Or it can also be placed up, organized in an array in this way, that you have a slice 1, slice 2, slice 3, and then we have to have a fill 1 like this. So it's like making a mosaic of different slices. Sometimes it's helpful, but if you have 2000 by 2000 slices and start doing mosaic of that, it's getting pretty big. So think twice if you do that. Then we can also have multiple values on the measurements. So for example, if you would work with alpha transparency and intensity is the typical one working with pictures. But physically we can also look at, for example, magnetic vectors, which have 2 directions, and then you would have a multiple or 3 directions. Then you would have actually multi-dimensional values on each position. And then you can have tables like this. What you also can have, here is an example of what it can look like. So we have intensity and we have transparency, but it's maybe sometimes difficult to look at it like this. So you may want to combine them somehow. And combining is done like this, for example. Let's see if I can get that one up. No, to convince it. So, so we have a large value. So large is white, and black is a small value. And then we can scale the sizes of these blobs based on one value, and then we can put different colors on them as well. And that gives you a way of visualizing multi-valued pixels. Then going even further on this is to go into hyperspectral imaging. So let's say we measure a spectrum on each point in the data. So looking at this image you have here, you can see these blue dots, and they correspond. I hope you can see them down there. That's not good. Let's bring it up like this. So you can see all these dots. They actually are spectrum measurements of light response in this sample, and then from that you can also work on. So this is from some kind of microscopy. In neutron imaging, we actually also look at multiple spectrum, and we look at diffraction patterns from different, mainly metals, and we can nicely do material analysis using that. Let's see, next one. Then we can look at each of these points. Then you can see here that there are different spectral responses depending on where you are in the data. And this is then something that you have to use. So you have to characterize these response curves and make conclusions about the sample in it. You can probably see that there are some, they have very similar shapes, and then there are some that are outliers in this behavior. So how we get our images, as in principle, a typical chain is that you have some kind of light source, a sample where this light source is shining through or shining at. You get a reflection or you get a transmission image. In tomography, it's usually a transmission image, and from that you get a response that is then captured by a detection system. There can be different ways of doing this. So it can be different interactions that you are talking about. You can have electron shell level response. You can have electron density. You can also have the configuration of neutrons and protons in a nucleon for each element. That gives a response. The response itself can be absorption, that the incoming impulse is absorbed completely. It can be reflected, can be scattered or phase shifted, or can even emit new information. And the detection system, well, the basic one is actually your eye. Maybe not so good if you work with ionizing radiation, but anyway, and then you can have films. But what is usually done in tomography system is that you have some kind of a digital detector, could be CCD, CMOS, in combination with a scintillator, which converts the incoming excitation into visible light, and the visible light is then captured by a camera. So that is the typical way of acquiring the data. And images, they come from different places. Down here you have a table of different sources and what kind of impulses, the characteristic of them, and so on. So this gives you an overview of different kinds of modalities. What we are going to see in this course mainly are data from X-ray and neutrons. These are the ones I'm working with mainly, and that is how the data is produced that I'm going to show mostly. Then there are different ways of acquiring the data. You can do it the traditional way, by optical imaging or microscopy, using visible images, but whoops, that is. Then you can also have a different acquisition system that produce something, some blurring, and you need to reconstruct the data before you can actually work with it. So you can see here, this one is measured and it's a bit blurred, and you have to do something to the data. So in this case, it would be some kind of deconvolution before you can see what it is. In computer tomography, you acquire a lot of projections around the sample, and then you have to do a computational step that inverts the projection data into the volume that you actually want to see. And that is the indirect or computational imaging. Sometimes you measure actually not even in a normal interpretable domain. So it could be that you measure in the Fourier domain, and that information needs to be transformed before you can see the original object. This one is pretty hard to interpret unless you're very good in interpreting Fourier transforms, which maybe not so many are. And for the layman, it's impossible. And then what we typically do is that we have this system where we have a light source looking at something that produces light going through or reflected, which is going through a lens, and then it's captured on the image plane. Or you can make it more complex. Then we look at, for example, tomography system, where we have first of all the light source that produces some kind of beam profile, which is absorbed through the sample, and there is some kind of propagation convolution effect in it. And then we have also optical transfer functions through the optics in light or in the radiation type that is emitted. And finally, we have some detector which also introduces some noise. And down here, I was hoping I could see the whole slide. Give it to me. No? Yeah, there it is. So in all, it's a pretty complex system that puts together all the information that we have. And this down here is even going over colors or multi-spectral information. So Another one is also indirect imaging using microlenses, where you have several microlenses. You can read how that works in this light field photography. And it's pretty cool because using information from this kind of system, you can actually define the depth of focus computationally after you have acquired the data. So you can really run through the focus points computationally. There are also other ways where you have mechanical sensing showing surfaces using surface topography, which you, for example, do in atomic force microscopes. So these are different ways of computational imaging applications. Then we come to the image analysis itself. So we have produced our images. Now we want to analyze the images. And there are different approaches how to work with the images. We have experimentalist view of it. It's driven by the problem. I want to see how waterfront is moving. It's going top down, and usually there is a real model behind it, so you can really follow the behavior by some kind of model. So it could be, for example, cell counting, porosity measurement in the sample. Then we have the computational computer vision approach, where you have a toolbox of many different filtering methods, etc., and you look for different features that these filters can extract, and then you look more into how the image is built up in order to do it. So sometimes you even engineer some features for solving the problems. Example of that is edge detection. So you have a filter that actually enhances the edges in the image. If you do face detection, you do even more than that. You have multiple filter kernels to extract different features in different regions of the image. So you actually produce new images in order to do the analysis. And then the deep learning approach is going actually towards the more modern techniques. It's very popular in analyzing images. You probably see it every day when you try to search for images in Google. You can look for something and it actually finds it based on label or also on the image content. So it even looks for similar images based on the image content. So it's result driven. Inspired by biology, so the way the brain is working and the vision of the eye is working. And actually it takes the image processing and analysis from a different approach, starting out from scratch. It can be used for giving images captures. So the typical one is in machine learning courses is always saying this is a cat, this is a dog, this is whatever, a car. And it's also good to identify unusual events. Often in imaging experiments, you have a very unbalanced problem. So you have a lot of background, which is confusing, and then you have a tiny little distribution that corresponds to what you want to see. So right now I have a student who is looking into segmenting roots in soil. And roots are like, say, part in 1,000, so per mil of the data is representing roots, and the rest is just, or even less, and the rest is soil or background or whatever. And all that information makes it hard to separate what is what. And this is also where the deep learning approach is very useful. So, going to science. In the end, there's a reason why we do our images. We want to get some answers. We know we have this sample, it behaves in a way, but we want to know why, or we want to at least anyway look for a way to test the hypothesis that this model is actually doing what it's supposed to do. And as normally when you have images, it's visual information. So what you normally do is just to look at it. Well, there is something happening, there is something happening, but it's still qualitative. You can say this has more of that or less of that, but you can't give it a real number. Well, and that is where the quantitative information comes in. We really want to set numbers of, for example, how many cells are there in this one, how many cells are there in this one, what is the cell shape, where are they distributed, etc. So we need to develop metrics to measure what we want to say, to confirm our hypothesis. And that is not so easy, actually. That's actually the frustrating thing about image processing. The eye can easily tell, well, there it is, but tell the computer how to do it, and tell the computer to do it always the same way. That is the problem. And there are a lot of algorithms which also indicates how difficult the problem is. Also, only the problem of segmenting an image into different classes. There are so many methods, algorithms to do it, and that gives the size of the problem that it's not very easy to do this. There is, of course, a standard pattern that you can follow, which gives some reasonable result, but still, it's not straightforward. And with more or less knowledge, sometimes you start just playing with the tools you have, and you may be happy and lucky to find the right result. The better way is actually to know the exact procedures how to do it. But it's not always people not working with image processing doing this, but it's more like clicking around, seeing, oh, yes, finally I got something, but they can't motivate why they got it. So, here's an example showing why we want quantitative. It's a classic example of visual illusion. Which of these center boxes are brighter? That's the classic illusion. Well, in the end, both are the same, actually. But just depending on the context, the eye interprets it differently. And here's another one, which is also a bit annoying for the eye. If you have this kind of step ramp, it looks like you're a little bit brighter on this edge than on this edge, but still it's a constant gray level within the whole bar here. So it's very difficult for the eye. It has some kind of edge enhancement feature built in, and that makes it this illusion. And another thing is, actually that one I want to make it a little bit smaller. So, what we mean, what we want, and how we should work. There are some words that are reoccurring all the time. It's reproducibility and repeatability, and often it's more about being able to repeat what you have done several times instead of reproduce what you have done. It's very expensive to obtain data, so sometimes it's better to recycle someone else's data, and that is the point where also the open data comes in. And the other thing is, if you have made a publication and someone kind of is uncertain of what you have done and want to understand it, they actually want to pull the same data through the same analysis that you did and come to the same conclusion. And reproducibility is a bit different, because then you actually have two parallel experiments. Can even be different experiments, but they want to confirm the same hypothesis. This is much harder, and usually it's hard to claim that you have to do it in this way. In particular, when you work with image data, it's a very hard one to handle. And this is this in text essentially. So the question is how we can keep track of what we have done, because that is the key point in the repeatability. As one thing is to work with well-documented steps, so you know exactly what you have done. And for this, actually the Python notebooks are very useful, because then you can write the text. You can even write slides like I have done here. And then you can step by step see what happens when your analysis goes on. And the other thing is, of course, writing clear and understandable code. When you're experimenting or trying to find something, usually the code looks pretty messy, at least when I do it. And then after a while, you come to a point, yeah, this is the way I want it. Then it's about time to also clean up the code, so you have clean steps that are easy to follow, and also using good variable names, maybe comments at some places, or even if you do a notebook, then you can even add a little text describing this is done because of this and that. I'm using these and these parameters because I want to do this. And with that, you more or less have a full report of your experiment within the same document, including the analysis. The other thing, now I have only talked about what can be done or why we should do it, etc. And also I mentioned that, well, we have a lot of data, and a lot of data means the computer or someone has to work hard. And Moore's law claims that the number of transistors in a CPU, they double every 18 months. That has been pretty good for many years, but at some point it flattens out. For example, the clock speed doesn't go beyond 4 gigahertz. That's physically limited. I think in the end it's about speed of light that prevents it, so we can't go faster. But the number of transistors, they still increase. And why is that? That's because we add more and more cores in the CPUs. So a core means that you have several CPUs, and that is a good help, because you can mostly in image processing tasks you can parallelize your processing, and that's a good thing. Because you can repeat the same task on multiple units, and by that you will also get a good speed up. Some cases the speed up is not so good. If you write bad parallel code, it's even slower if you run it on 8 cores than if you run it on 1. Can happen. Then it's time to go back in the design. But typically you can have something like 75% of the number of cores as a speed up. That's pretty decent, actually. If you can get better, of course, it's great, but then you put also a lot of effort into it. Then you can also go on the big scale, go into clusters, and that will then do a lot of speed up. And that is actually what is needed when you do machine learning on large image data sets. Sometimes it's the only way of actually processing the data. Something that I didn't mention here is that the graphics cards, they're actually excellent parallel computers. So you can do a lot of speed up using the graphics card, and many algorithms also in the machine learning packages provided in Python, they are actually working a lot on the graphic card. So then you can have something like 2,000 cores working in parallel, dedicated to do the processing, and you have a huge speed up for little investment. But then to scale it up yet again, the clusters, they can even them can have GPU nodes. And that is actually a thing that when you want to do computation on a cluster, it's pretty expensive to buy, say, a stack of 20 or 100 computers. And as an alternative, there is the cloud. And for example, Amazon, they provide cloud services where you can buy in time for doing cluster computations. Cost some cents per hour, depending on how expensive, how intense how strong the computer is that the system is based on, and how many nodes you want to use. But many of these services, they can provide you with parallel computational power for decent money. And well, here's an example that a PhD student is 400 times more expensive per hour than an Amazon EC2 machine. So if you want to wait, of course, but it's pretty expensive to wait, so maybe it's better to invest some money into computational power in this way. Here at ETH, there are of course also clusters that you can, oops, that wasn't meant, that was a bit too fast, that you can also probably reserve time on different projects. I think I skipped one slide here, something went out. Yeah. Yes, I missed that one. So, just to show the effect of using parallel code, let's make a soup. So, what you do when you make a soup? First of all, you buy the vegetables you want to have in the soup. Then you go to the butcher and buy some meat. Then you chop the different vegetables in pieces. Then you start boiling water. And, well, when it's boiling, then you add the vegetables, and then you wait some minutes, and then you add the meat, and after a while you have your soup. Clear sequence. But usually, this is not the way it's done. You can do it a little bit smarter, because in some cases you can take some steps in parallel and make it more efficient, and in that way you have your soup probably a little bit faster ready than you would have if you would do it in the sequence. And this can look like a workflow like this. I think this is something that should be, nope. So looking at the graph for that, then you can see we have a long chain of stuff that needs to be done, one after the other. But if you do change the workflow into the second recipe, then all of a sudden it looks like this. So you see here that you have some parallel workflows. So you can do some stuff in parallel. You can buy the vegetables while the water is heating up. Well, that's optimistic, but anyway. And then you add the vegetables, and while you do that, or before you do that, you can also buy some meat, and then you add the meat. So you can see here that you have made a more compressed workflow, and that is actually what you are going for when you do parallel computing. You try to do as much as possible in parallel. In image processing, it's usually very simple, because you can take the image and bring it into blocks. So you have, let's see if that one wakes up. Yep, it does. So if you have an image like this, you can divide it into different blocks like this, or you can divide it into blocks like this. And then you can run the same code on all these in parallel. And then you have a good speed gain. In theory, because I don't know how many of you have advanced programming experience, but after a while you notice that the cache is messing it up for you and can slow you down. So you have to do smarter segmentations than just these blocks. But in the end, it's about bringing it down in smaller blocks, which the computer can work with easily in parallel. For that, there are tools. So we have something that calls directed acyclical graphs. And there are a lot of toolboxes that use this. And that's actually a tool set that allows you to split the task into subtasks. And one example here is that we have a simple calculation. Very simple. You have an image that is producing zeros. It's not so exciting actually. But going on, then we can make a little bit more fun. Then we create, oops, it wasn't meant to. Then we create two images, one with ones and one with zeros. We produce some data blocks, and these data blocks are added into a single one, and you see that you start building up a graph like this. Still, it doesn't really make sense if you have a single image like this, but it gets more exciting. So we still have two parallel workflows. Still not so much motivation for it, but you start seeing that a more complex system can be created. But now that you go big, then we come into more interesting thing. And here you can see that I create the zeros, but also that I create different chunks. So here I have chunks of 512, and the whole image is 1024. And the result of that is that now it's split up into 4 parallel processes. And that is segmentation or separation that we do in the beginning. And then afterwards the graph will run on as many subblocks as we want to do. And that could be even split into 256, or yeah, on this one, and 256 on that one. And that would create us even more parallel threads to work with. And this is the way that machine learning tools are building up their different processing units. So if we start doing the processing, you can see that it creates a lot of graphs, and in the end, these graphs, they will run in parallel on the computer or the graphic card or the cluster or whatever you set as target unit for the processing. And well, then it can get even more complex when you do some matrix multiplication. Or we can do, yeah, it gets more and more complicated, the graph at least. But the interesting thing is that you can subdivide your blocks into smaller ones that can be handled by each CPU. And well, now we get really big. And here is a bunch of, so this is matrix multiplication of 2 images plus 1 times 2. And if you want to follow, you can follow the graph like this and see what the different elements are doing. And yet another one, let's see, so okay, there it comes. And, oh, that one wouldn't like to work. Okay, I did something stupid up here. Let's go back to the same size. So some wants squared blocks, so that was the problem here. So now I'm running a filter, and the good thing here is that now I'm using a package called Dask, and in Python there is a large library called NumPy, which is numerical methods for Python. You have essentially what you need in it for numerical calculations. Now when you add Dask in front, then you have the whole parallel framework on top of the NumPy, which is very convenient because then you can easily change your first test code, which was done in NumPy, into parallel code with few steps. And now I'm actually at the end. Let's see. Yep, that was it. So as a summary for today, I've been talking about, first of all, that we produce images and we want to analyze them in a reproducible way. And when we produce our images, it can get a lot of data. So with that, we certainly want to have the computational power to work with it. And the best way of doing it is working in parallel on the data. So, well, that concludes my lecture for today. Thank you.